Okay, YouTube, in this video we're going to explore for the first time how to solve quadratic equations in one variable. That is, these are equations that are written in the form ax squared plus bx plus c equals 0, where a, b, and c we say are all real numbers, and we don't allow a to equal 0. And the reason why we don't allow a to be 0 is essentially because if a is equal to 0, then we wouldn't have this statement right here set equal to 0. We would have a statement that says bx plus c equals 0, and this would be some linear equation in one variable. So when we talk about quadratic equations in one variable, we want to be very specific. We are solving equations where our quadratic thing is sometimes written in standard form here, but that it's set equal to 0. So must equal 0. Okay, so that's kind of a big deal because there are three methods that we're going to explore for solving quadratic equations. One is by graphing, the other one is using square roots, and then last but not least by factoring. And in two of these here, we'll always consider this equation to be equal to 0. So in this video, we're going to look at how we solve a quadratic equation by graphing. So by graphing, looking at our little chart over here, it says find the x-intercepts of the related function y equals ax squared plus bx plus c. So the idea is if we're going to solve this equation right here, it's really just, it's hard to get x by itself because we have both an x to the second and an x to the first term. So what we're going to do is we're going to graph the associated equation y equals ax squared plus bx plus c. We'll just go graph this. And what this says here is find the x-intercepts of the related function. So what I want to basically get across is this. When we solve this equation here, we're kind of going and graphing this equation right here where we have a y, but when we solve it, we're looking for the x-intercepts because what we're essentially doing is saying, well, let's let this y value be equal to 0. So if we had some graph that is some parabola here, and we say, let's go solve this equation, we're saying what we're really doing is we're looking for the two x values. We'll call this, say, x1, comma 0, and we'll call this x2, comma 0. But we're looking for the two x values, if there are any, that run into our x-axis, because when we plug those two x values in, look what we get for the y value. We're essentially saying that solving this equation, we could do it by finding those two x values because y would be equal to 0. So again, it says the first way to solve the quadratic equation is to examine its graph. Because we are solving an equation y equals ax squared plus bx plus c where the y value is equal to 0, that is, we've set it equal to 0, the whole equation, then we're really just looking for the x-intercepts of the graph. So I say that this can be accomplished more easily by rewriting our standard form equation into the intercept form y equals a times x minus p times x minus q, where we already know that p and q happen to be the intercepts of this equation. So we do this by factoring the original expression. So let's do this. We say trying to solve this equation right here, y equals x squared plus 3x minus 10, it would be more easily accomplished if we go graph y equals, and what we'll do is we'll factor this. Now I notice that this is a factorable expression, and if I could think of two numbers that multiply out to be a negative 10 that add up to be a positive 3, I could think of a positive 5 and a negative 2. So our factors here would be x plus 5, x minus 2, and we would say that our a value here in this intercept form happens to be 1. So graphing this here, I know that this hits my y or my x-axis at positive 2, as a matter of fact, remember p and q are backwards, and at 1, 2, 3, 4, negative 5 right here. So our parabola, its axis of symmetry, remember, would be the average of these two p and q values. So if we take our positive 2 and negative 5, and add those together and divide by 2, we would come up with this equation here that says negative 3 over 2, or negative 1.5, would be our axis of symmetry. So our axis of symmetry would run directly between these two values right here. And then to find the vertex, we would just plug negative 3 halves into this equation. So we would say f of negative 3 halves would be equal to 3 halves negative plus 5, and then 3 halves negative minus 2. So here we would end up with this. We get negative 3 halves plus, if we change this to halves, we get 10 halves. We would get negative 3 halves plus 10 halves. And over here we would get negative 3 halves. Now changing this down here to a 2, we would get negative 4 halves. So essentially we end up with this here. We get 7 halves times now negative 7 halves, which gives us negative 49 fourths. And using our calculator here, we could just type this in. We would say 49 divided by 4 basically it's about negative 12.25. So our vertex is really far down here, and we could graph this parabola. We didn't have to factor it to graph it, but certainly the reason why I wanted to factor it was just to basically say, look, in this factored form we already know the x-intercepts of this graph to be a negative 5 and a positive 2. So we would say that the solutions to this equation here, x, are negative 5 and positive 2, and we get two answers, and it would be easy to plug this back into the original equation here and see that we get 0 in either instance. So looking at this one over here, looks like we have 2x squared plus 18 equals 12x. The very first thing we want to do is set this equal to 0. So I'm going to rewrite this up here so I have a little bit of space, but I have 2x squared. If I subtract 12x over to the left side, it would be minus 12x plus 18 is equal to 0, and now this is written in standard form. So to factor this, let's start by saying, well, I already noticed that everybody here has a common factor of 2. So if I factor that 2 out front, now I'm left with x squared minus 6x plus 9 is equal to 0. And I would say, well, what could I factor out here? What could I factor this into so that I get two numbers that multiply out to be a positive 9 and add up to be a negative 6? And I can think of this would have to be a negative 3 and a negative 3 that would do so. So this being an intercept form, what I notice is I get positive 3 twice here. And because our a value is actually positive 2, the only way that my parabola could hit the x-axis just one time and not twice or no times would be if this is the vertex. So I could say that really I could go up 2 over 1 and say this is our parabola here. But the bottom line is, once we graph this, we notice that the x value, oh, I can't believe I did that. I can't count. Here's 2. Actually, no, it is 3. It is 3. I had 2 on my mind here from the a value. But we see the only x-intercept that this graph here has is that x equals 3. So we would say that that's the solution to this equation up here where we've set everything equal to 0. So the last thing I've done here is this. I actually went and I plugged these two equations in for y1 and y2 in my graphing calculator. You can see x squared plus 3x minus 10 here. And I'm going to go turn this graph on. So I'm going to go hit enter here. And when I hit graph, what I want us to see is that we do indeed get x-intercepts at negative 5 and at positive 2. And those are the solutions to this equation right here. And when we go back in, notice that this time when I graph this second equation, 2x squared plus 18 equals 12x, we had to first set it equal to 0. That was the first thing we did here. And so when I set that equal to 0, I had 2x squared minus 12x plus 18. I'm going to go turn this graph on. So we'll turn that first one off. We'll go turn this one on and graph it. And you can see that we get this graph that comes down and hits at x equals 1, 2, 3 right here. So its solution is 3. So the bottom line is, if you want to solve a quadratic function, what you do is you graph the related function associated with this, and you find all the x values that would cause this y value to be equal to 0. In other words, you find the x-intercepts. Cheers.